Well, hello everyone. So I'm going to be recording the next couple lectures. Okay. Um, all right. Well, let's begin. So let me screen share first. And here we go. There. Okay. So now where were we last? We had just looked at, the simple harmonic oscillator, and we had all these, we looked at what the wave functions look like, and we were looking at, and so then this was the last page that we were on, okay? And um, that's what the wave function for the nth energy level looks like with the Hermite polynomials, right? So these are called the Hermite polynomials. Okay. Now, what we were doing was looking at the uncertainty in the position and momentum for the ground state. And we wanted to show that the ground state of the simple harmonic oscillator is just a minimum uncertainty state. Minimum uncertainty state means that the product of the uncertainties in the position and momentum is actually going to be equal to h bar. And I think I missed um, a factor 2 there. So let me stick it in. All right. So this should be um, factor 2. So h bar over 2. Okay. So minimum uncertainty state is where the uncertainties are each equal to square root of h bar over 2. All right. And we looked at, what we call, we found a way to depict them. All right. And so delta X, delta P is there. Um, and so we talked about modes of an electromagnetic field mimicking the X and P, right? So for a thermal light source, well, that's what the fluctuations look like. They might not be as symmetric, not like a circle, but in general, you expect the two to be equal. All right, now a minimum uncertainty state is where you have each of those fluctuations equal and square root h bar over 2. On the other hand, in a squeeze state, you can go ahead and squeeze the fluctuations in one of them as far below square root h bar over 2 as you like, as much as the power of your instrumentation allows you, right? And of course, then the fluctuations in the other one go correspondingly up. All right. So this is what we were discussing. Now, what I want to show to you right now is that uh, the ground state of a simple harmonic oscillator is a minimum uncertainty state. Okay, so how do we do that calculation? So what we're going to do is um, see for ourselves, and it's a simple enough calculation. Um, so what we're going to uh, show is, so here's the deviation of x from, the fluctuation in x, the operator, is defined as the operator x minus its average value, its expectation value. The fluctuation in the momentum is the momentum operator minus the average value of the momentum operator, or the expectation value of the momentum operator. The uncertainty in x, how would that be defined? Um, so this guy here is equal to uh, the uncertainty in X. Okay, so please note that that's the uncertainty in the expectation value of the operator. So these are things that you actually measure. Okay, and the uncertainty in this is going to be uh, defined as first you find the expectation value of the of this guy squared, and then you take the square root to find the uncertainty in this operator, and this will be your delta x. So this guy here. Okay, so that's this delta x. So that's the uncertainty in x. What we mean is the uncertainty in the measured value of x, right? And that's of course this guy. And to find the uncertainty in the measured value of x, first you have to find the fluctuation of the operator, take the square, take the expectation value of that, and then the square root. And that's what this uncertainty in the measured value of x would be. Okay, so let's just calculate it. Delta, so I'm just building this guy up. So as I wrote up there, okay, that's the deviation in the x operator. So now the next step would be to, I'm just building this guy. Okay, so this squared, right? And that's equal to squared. Okay, and so I can expand this out. Get that. Okay, plus. All right. And now I need to take, so first I did that, and I did this. Now the next thing would be I take this squared deviation and I take the expectation value. And then finally I'll take the square root. Okay, so now the expectation value, so an expectation of x squared, okay, minus, now the 2 is a scalar, so is the expectation value of x, that's just a number. And then when you take the expectation value, you have to take the expectation value of an operator, and only this is the operator part. So I get that, right? Plus, and this is just a number, so it just stays as it is, the last term. Now you see that there's a minus, well, let's just a minus 2 expectation value x squared plus expectation value squared. So you just get that, right? Okay, so that's what I have. And now I can try to see what these would be. Well, clearly, the expectation value of x is just, we'll see that it's 0 because remember, the operator x in a previous slide, we know that it is written in terms of the a and a dagger like that, right? And so if I find the expectation value of x, then I'm going to have square root 2h bar per m omega 1/2. And the expectation value means that between n and the operators I have are a plus a dagger, right? And you can see right here that, what you can see is that, so I said here clearly, well, this is equal to 0, okay? Because the expectation value of the A operator is 0, as is the expectation value of A dagger, right? Why? Because A acts on the n state to give you a n minus 1 state, and n minus 1 state has no overlap with n, right? So if you want to, so that's because n minus 1 is 0, that overlap is 0, as is the overlap between, in this case, A dagger gives you a n plus 1, okay? So that's why. So this becomes 0. So that means that this thing goes to 0, okay? So now what I have is we are 10, what's the date today? 28. Okay, and so, therefore, expectation value of the deviation of the operator x, the square deviation, the expectation value is just the expectation value of the operator x squared. Okay. And so now we can evaluate that using the same idea as above, convert it to A and A dagger, right? So this would be, so I'm looking at this. So now I have a squared, right? So 2h bar over m omega, square of that. And then there's a 2, so a 1 over 4. And then I'm left with the expectation value between n and n of x squared, right? So that would be A plus A dagger squared. Okay. And this guy is going to be A squared plus A dagger squared plus A dagger plus A dagger A. Now, of course, so clearly the expectation value of A squared is 0, right? Because A squared gives you a n minus 1, and then first A operates on n gives you n minus 1. Another operation of A gives you n minus 2. And of course, n minus 2 and n don't overlap, right? So it's 0, as of course is also the case for A dagger squared, right? And so it's because n plus n minus 2 is 0. So this goes away, that goes away, and you're left with A dagger plus A dagger A. Now this, of course, is just the number operator. And so I know that n, the expectation value of A dagger A, n is just the number operator n, and that's number operator acts on the number state n to give you n, and then you're left with that, which is 1, so that's n. Okay, so this one was easy to do, the A dagger A. What about the AA dagger? Well, AA dagger, you got to use the commutator A dagger equals 1 to find this expectation value. Okay, so we can do that. And what would we find? Because the because this is easy, so you can replace, this tells you that A dagger minus A dagger A equals 1, which implies, and this is something we use a lot, okay? So we just put that in here. 1 plus A dagger A. So you get from the 1, you just get 1. And from the other one, A dagger A, that's your number operator again. So you'll just get N. Okay, and now we put all these results into the original equation that we were looking at. Okay, so this guy, so you have a 1/4, a 2h bar, m omega, and from the expectation value, you got a n and a 1 plus n, so that's 2n plus 1. Okay, so this tells me, and now in the end, I will take a square root. So therefore, delta x, the uncertainty in x, is equal to the square root of the square deviation. Okay, and so this is equal to square root of, so this 2 goes with that. So you have a h bar over 2m omega. Okay, so you note that the uncertainty in x, it grows with the number n. Okay, that's interesting. All right, so we got that. And then similarly, we can calculate the delta p. Okay, so similarly, for delta p, okay, and this again is equal to the square root of the deviation of square deviation of the operator p, and there you go, right? So that's what we're trying to calculate. And so again, you will get that proceeding similarly as we did before, you will find that this is just p operator squared, right? Because the p operator expectation value is 0. Why is that? Because remember what p was defined as earlier? It's just n. The p is a minus I 2h bar m omega times a minus a dagger over 2. Okay, so again, you have a and an a dagger, and for exactly similar reasons as before, you will get all of this to be 0. All right, so now this leads you to just the operator p squared. So that's a minus I squared, right? So the minus minus goes away. I squared gives you a -1. And then the square root of 2h bar omega squared gives you that. The 1 over 2 gives you a 4. And then you have a minus a dagger. So actually, and squared, right? So this is going to be n a minus a dagger squared. Okay. And so we can expand this out, and you would find that that would be an a squared plus a dagger squared, a minus a dagger minus a dagger a. Okay, and so once again, exactly using the same logic as we did here, the a squared expectation value, the a dagger squared, these would give you 0. Okay, the expectation values would. And then this minus sign cancels with that minus sign. So therefore, so this minus sign and these minus signs cancel. Okay. You're left with the h bar m omega over 2. And you have n a dagger plus a dagger a n. But we evaluated this up here, right? That's what we did up here. And we found this to be 2n plus 1 as evaluated above. Okay, so your answer, therefore, let's go to another page. Is this guy is equal to h bar m omega over 2n plus 1. Okay, and so you can compare it with the delta x squared. And so therefore the delta p, which is the uncertainty in momentum, okay? So whenever we say momentum, not the operator momentum, just momentum, we are referring to the measured value or the expected value of the momentum. So this is like that, right? So same for when we were talking about x, uncertainty in x, that means in the measured value of x. Okay, so now this would be square root of what we just calculated. And so therefore delta P is equal to square root h bar m omega over 2 2n plus 1. This 2, okay. So now we can put our results together. So delta x delta P is equal to what? Delta x delta P. So I have the delta x sitting up there. You can see things are going to cancel, right? Times square root 2n plus 1, square root 2n plus 1. So I'm going to get 2n plus 1. Okay, and by the way, this guy grows with square root of n. This goes with square root of n. Okay, the product will grow as n. But anyway, let's get the other constant in there. Square root. Okay, and so things cancel. What cancels? You have the m omega, the m omega. Okay, and so you're left with h bar, and you get a 2. So this guy grows with n. All right. And then for the ground state, n equals 0, we have delta x delta p is equal to, n is equal to 0, so you have h bar over 2. And so that is a minimum uncertainty state. Okay. So yes, that's what we were wanting to show, that the ground state for the simple harmonic oscillator is a minimum uncertainty state. And that concludes our discussion of simple harmonic oscillators. So I'm gonna end this segment this recording and go look at if the recording actually worked. All right. And then I'll be back with another segment for you.